Stories. In this video, I'll be discussing the numerical of balancing. So, in this numerical, we have several masses which are not at the same plane. Okay, so let's read out the numerical here. A rotating shaft carries three unbalanced masses 5 kg, 3 kg, and 2 kg at radial distances of 75 mm, 80 mm, and 55 mm, and at angular positions 45 degree, 135 degree, and 240 degree respectively. So we have their masses, three radiuses, and their respective angles with the horizontal. Okay, these are given. Next, the second and third masses are in planes of 200 mm and 375 mm from the plane of first mass. So the planes, distance of the planes for second and third mass from the first mass is given. Okay, the angular positions are measured counterclockwise. This is an information where we count this angle in counterclockwise direction from the reference line x-axis along x-axis and viewing the shaft from first mass end. So these are some informations. So we'll go to the problem again. Now see, this is the shaft. Okay, this diagram is given. It may or may not be given along with the question, but if such type of questions diagram is not given, you may construct this diagram. Okay, so you know first mass m1 and the r1, this radius is given, and the angle with the horizontal, this 45 degree is given. Okay, similarly for second mass, angle with the horizontal is 135, the mass value and the radius value is given. For third mass also, mass and radius is from the distance from its axis of the shaft to the point, the center point of this mass, and the angle 240 degree is given with respect to this horizontal line. Okay, 240 degree. Now the distance from for the second mass from first one is 200 mm, and for the third mass from first mass is 375 mm. Okay, these distances are given. Okay, that is, these are the I mean the distance between the planes. Okay, first plane of this mass and plane of this mass, plane of third mass, all planes are parallel to each other. Okay, and the distance between the planes are given. Now let's read the question further. So the shaft length is 800 mm between bearings, and the distance between the planes of the first mass and the bearing at that end is 225 millimeter. Okay. Determine the amount of counter masses in planes 75 mm from the bearings for the complete balance of the shaft. The first counter mass is to be in a plane between first mass and the bearings, and the second mass in a plane between the third mass and the bearing at that end. So you have to understand this part. So you see the shaft length, total length between the bearings is given. That means from the bearing from here to here, first bearing to last bearing, that is 800 mm. Okay. Next, you see distance between the plane of the first mass and the bearing at that end is 225 mm. So first mass and the bearing, the distance is given as 225 mm. Okay, then determine the amount of counter mass in plane 75 mm from each bearing. So you have to place two balancing masses, that is away from 75 mm away from each bearing. So from first bearing 75 mm away from that, we'll have to place a counter mass. Okay, let's mark that point as C1. Okay, and another counter mass 75 mm be again away from the other bearing, that is, let's mark that point as C2. So we have to place two counter masses. That means let's write these masses as MC1 and MC2. MC1 will be placed here, MC2 will be placed here. Okay, at the radial distance of RC1 and RC2. Right. Okay. Now, okay. Then, so the first counter mass is to be placed in a plane between first mass and the bearing, between first mass and the bearing. Here we need to place the first counter mass, and the second counter mass Okay, second mass in the plane between third mass and the bearing. So between third mass and the bearing. Okay, here we place. Okay, so every information is given. So take radius of balancing mass at 75 mm, s 75 mm at reference plane. RP means reference plane, and 40 mm at the other plane. That means you have to take one of them, one of the plane balanced mass. See, this is a balanced mass plane. This is another balanced mass plane. These are unbalanced masses M1, M2, M3. Here you have to balance these two. So you can take either of them as reference plane, RP, reference plane. If this figure is given in the question only, okay, then reference plane will be mentioned to you. If it is not mentioned, most in all almost all usually in general, you take the first, the C1 as the reference plane. You can take also this part as reference plane, not a problem. Okay, but this can also be taken as reference plane, and we can measure the distances from the reference plane, okay, for each of them. Okay. Now you see, it is given that the radius of the balancing mass at the reference plane is 75 mm for this part, okay, and you see 40 mm at the other plane. That means RC1 and RC2 is given. What is RC1 and RC2? You know, you have to place a mass MC1 at a radial distance of RC1. We also place a mass MC2 at a radial distance of RC2. So you have been given with the RC1 and RC2. What you don't know is MC1 and MC2. These two you have to find. Okay. So we need to place two balancing masses in C1 and C2. These two, and the values have to be found. So now what you have to do is, this problem is different. Here we have been balancing different masses, okay, several masses at different plane. What you have to do is, you have to take all the masses in your reference plane. Okay, that means you have to take this sorry, not the masses, sorry, the forces. Now see this M1, see this one M1 R1, this will cause a centrifugal force outward, this will cause a centrifugal force outward, and third one will also cause a centrifugal force outward. So if you take this one, this force, okay, here, okay, and take this force, the second one here, third force here, okay, yeah. And how to take these forces we have learned already. See, to transfer a force, see, was there somewhere, just a moment. Actually, how to transfer a force is, you have to multiply the length. Okay, so here you see, here it was somewhere, I need to find out. Yeah, this one, transference of a force. So this force is there, M and R. If you transfer the force to this at a distance of L, so what you have to do is, you have to multiply L with them. So MR into L, that is what you have to do. Okay, so here we will see that how to do it. Okay, so finally after transferring all this, we have to find the resultant, and the resultant will be equal to the balance masses. Okay, so yeah, one more thing, here also we'll have some balance mass that also need to be transferred here. Okay, and we already have that M1C1, okay, sorry, MC1 RC1, that will be present here. Okay, all the centrifugal forces must be balanced by some equivalent forces. Now let's find out, see what you have to do, how to start the problem is, you have to always take a reference plane, as you remember, and find the distances from the reference plane to each mass. This is the distance for the first mass. Okay, from here to second mass, what is the distance? You find out that. Okay, from here to third mass, okay, this one, what is the distance? Okay, these distances you must calculate. Okay, so these distances, and the fourth mass, that is the balanced mass from here to here also. Why do we need the distances? So that we can multiply them. Okay, now you see from figure LC2, this part, what is it? So LC2 is the distance for the from the from the balance mass at C2 point from the reference plane. Every distance will be at the reference plane. So this is actually LC2. So LC2 is total distance is 800. Okay, minus 75 minus 75 each side. That's why 800 minus 75 minus 75. We have 650. Okay, now we have this L1. L1 is 225, 225 minus 75. So see, L1 is, you see, from here to here, no, from reference plane to the first distance between first turn. So you know the total distance from here to here. So minus 75 will give you the distance gap between these two. That's why 225 minus 75. Here L2 is again, you see, L2 will be from reference plane to this one. So that is 225 minus 75, this gap plus 200. So see, 200 plus 150. This is the gap, no? So this is 350. Similarly, L3 is the distance from reference plane to this mass. So that is 225 minus 70, that is 150. Okay, plus how much? 375. So 375 plus 150, that is 550. So now we have the all the distances for all the masses from the reference plane. Okay, now we can calculate the couples. Now let's find out the couples. So for first mass M1, this is the couple M1 R1 L1. So we have got the value. Similarly, M2 R2 L2, M3 R3 L3. These are the couples for this M1 mass. We have found out the couple here. Okay. For M2 mass, we have found the couple here. Just multiply the length with MR value. So M1 R1, so multiply L1. L1 we have found, no? L1, what is L1 if you ask again? So this is the gap between reference plane and first mass. Similarly, L2 will be gap between reference plane and second mass. L3 is reference plane and third mass, and LC2 is the reference plane and C2 distance. This is gap. Okay, so that is what we have done here. We will use LC2 later. Okay, and also see, these are couples, we will need them, and we also need the value of M1 and R1. Okay, sorry, M1 R1, M2 R2, that is MR value. This is for static balancing, these are for dynamic balancing. Okay, so find out M1 R1 also, M2 R2 also, M3 R3 also. Now see, for dynamic balancing, this is the equation for dynamic balancing. Let's use it first, then we'll get the values of MR, MC, etc. So you know, summation of all these. Okay, let's go back to the analysis. So here we can see that how to do it. You see, we have to add these. See, M1 R1. Oh, sorry, this is static. So this is dynamic. See, for dynamic, M1 R1 L1, M2 R2 L2, M3 R2 L3 plus MC2 RC2 LC2. So omega square will get cancelled out. So this is what we have written in concise manner like this. Okay, so this is what you have to do now. Here you can see that in this problem we have done that M1 R1 L1 plus M2 R2 L2 plus M3 R3 L3. These are the summations of all the forces. Okay, these plus MC2 RC2 LC2. This is what we have done. Okay, added to this one. Now since I told you that you have to find out the components. Why components are required? Because the forces are, all the forces are at an angle with your, see, this is the force, right? So this makes an angle with horizontal. So to find a component of these forces, horizontal or vertical component. Similarly, for this force also, we need to find out the horizontal and vertical component. Okay. Similarly for a third, similarly for this one, we don't know where is the direction of the MC2 one, but let's assume anything, and we need to find out the theta also. Once we get theta C2 now, then only we will know the direction of this. Okay, that we will see, but we have to find out its component. Let's, by assuming the angle is theta C2. Okay, so we can directly write the horizontal components by multiplying cos of the angle of each of them with horizontal. So for this one, cos 45. Okay, that means M1 R1 L1 cos 45. So here you see M1 R1 L1 we have already found out, right? So we have just written the values multiplied by cos 45. Similarly for the second one, M2 R2 L2, the value is 84,000. So 84,000 multiplied by cos of 130. Whatever is the angle. So cos of 135, next one will be cos of 240 for this one. Okay. Don't worry about the signs of now, because they will be positive here, because our angle is anti-clockwise every time. Okay, anti-clockwise angle we have taken as positive. For cos of negative angle is positive only. So this side all of them are positive, 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 positive. And this one we don't know the angle theta c2. We have assumed the angle is theta c2, and we will keep it as it is. Theta c2, this is unknown. That's why we don't know the angle of this MC2. Where it may be here, it may be here, it may be here. Okay, anyway, we need to know that thing. We have to find out theta c2, then only we can get it. Okay, so this is unknown, others are known. So we will find out MC2 RC2 RC2, huh? It's not RC, RC2, this is RC, and LC2 theta c2. So we will see RC2 is given to you actually. LC2 is also known to you. Okay, how? Because this is given. LC2 we have found out, right? Here, this is, and RC2 is what? The radius of the second mass. So 40 mm is the value of RC2 given. For the first mass, that is RC1, radius is 75. These are the radius. No? Take the radius. So you have to, you know that RC2 and LC2 are known. So you can actually reduce this later, but let's first of all first keep it as it is, so that we can combine them together in your particular horizontal components as it is as a whole. So we can eliminate this angle first. So now you see what you have to do is vertical components, you just have to take the angles as sine. Now the value of this one will be MC1 R MC1 RC1 LC1. That means this one, oh sorry, not this one, M1 R1 L1 sine theta. So M1 R1 L1 sine 45. So this one will be, next one will be M2 R2 L2 sine 135. Sine 135. Next one sine 240. This is the angle is 240. And this one MC2 is unknown. RC2 LC2 will just write it like that, multiplied by sine theta C2. Okay, C2 is unknown. So we will have to find out this. So let's just keep it aside, and we know the values. We have calculated it as minus 491. This one here also, this is plus 48. So now what we will do, we'll have to square this. Okay, square this term, whole thing. That means square here and square here. Okay, squaring both the equations and adding. So this square, this left hand side square, okay, and this left hand side square. You have to also do the square in the right hand side, and then adding them and removing the square. So what you have to do, we'll have to take it as the root, and here this is square and this is square. So we get some value here by solving it. Now we are left with MC2 RC2 LC2. Here LC2 is known, RC2 is known. Just by putting the values, we can get the balance mass. Okay, so we have found out the balance mass to be put in the other plane other than reference plane, here MC2. Now we don't know where to put it and at what angle. So we need to find out the theta C2 in this case. So let's find out theta C2. This is the formula. How to find? Okay, you may be confused. How did we found out? So what you can do is you take this one divided by this one. Okay, so if you divide MC2 RC2 LC2 sine theta C2 divided by MC2 RC2 LC2 cos theta C2, so these three terms will get cancelled out. Okay, because they are the same. And sine theta C2 by cos theta C2 is tan theta C2, isn't it? Tan theta C2, and equal to right hand side value. This is this divided by this. Okay, so minus this 49158 divided by 48497. So if we find out from here, you find out tan inverse of this, you get minus 45 degrees. Now why minus in this case? This will be in this direction, clockwise direction, because of minus, because we have taken all angle positive in anti-clockwise direction, right? 45 in this anti-clockwise direction, 240 anti-clockwise direction. So we have got negative, that is minus 45. Okay, minus 45 is in this direction. This is the direction of MC2. So this is 45 degree in clockwise direction if you take. Now what will be the angle with horizontally in anti-clockwise direction? This is the angle. Okay, you see, from here to here. That means 360 minus this 45 or what. Okay, that you can find out. So here 360 degree, you can see 60 degree minus this angle, is 314.61. So that means we have to find out in this manner. Okay, all the angles are going in anti-clockwise direction. So here also this will be in anti-clockwise direction. So this is MC2. So the angle is this one. Okay, we have found this angle, negative one, but we have to find a positive angle. So 360 minus this angle, no, this will be 340. Okay, so we have got theta 2 also, theta C2. Now, okay, now we have to find out M C1 and theta C1. Okay, so let's use this static balancing equation. So static balancing equation, we know this equation from here. See, the static balancing equation we have learned here. Okay, summation of all M1 R1, M2 R2, M3 R3, whatever, plus MC1 RC1 plus MC2 RC. Okay, omega square will get cancelled out. So we have, this is actually the combined version of these three. Okay, and these two will remain. So we can write it like that, and then we find their components. So in this case, we don't write the lengths. We just write the values of M and R. So M1 R1 plus M2 R2 plus M3 RT plus MC1 RC1 MC2 RC2. This whole thing is known. This is known. This is known. What is unknown? MC1 and RC1. This is only unknown. So just first of all, we need to find out their components. So just now we have done. So what you have to do is you have to just take the cost terms everywhere. Okay. So we have assumed this angle as theta C1 and this is theta C2, we already know. So multiply cost terms of the particular angle with each of them. So you know M1 R1 we have found already here. You see M1 R1 found, M2 R2 found, M3 R3 found. Theta 1 is 45, theta 2 is 135, theta 3 is 240, and theta C2 we have just found. What is that? 340. Okay, so we'll just put them each values, cos 45, this one, cos 135, cos 240, this 375, 240, and 110. These are calculated, and this one MC2 we have just calculated. MC2 value is 2.66 kg. So I'll put 2.66. Radius is 40 given to you, and the angle is 340. So we are left with MC1 cos theta C1. So we will put it aside. MC1 cos theta C1. This is one equation. Similarly, we'll take the vertical component and we'll just multiply sine theta 1, sine theta 2, sine all sine terms with each of them. And we take their angles, respective angles. In this case, again, we don't know MC1, RC1, and theta, sine theta C1. So MC1, RC, and sine theta C1, we'll just keep it separately and we'll find out everything else. So we have got MC1, RC, and theta, sine theta C1. Now, how to find out these things? Just square and add. Square this, and add them. So MC1 RC1 cos square theta C1 plus MC1 RC1 sine square theta C1. So this MC1 RC1, if we take common, this whole square plus cos theta square plus sine theta square is 1. Okay. So that means cos square theta plus sine square theta is 1. So that's why this will have it as MC1 RC1. MC1 RC1 only. Okay, plus root over of these two square. This square, okay, this is square plus this is square. Okay, negative sign will become positive, and because of squaring, and we'll have MC1 RC1 is this. Now you have given in the question that the radius of the first mass, balancing mass at reference plane is 75. So RC1 is given as 75. So here we can see that this is 75. So from here, by solving, we can find out MC1. So the balanced mass that is required at the our reference plane is 3.56 kg. And where to place this mass, we need to know the angle. Okay. So we have found out the value, but where to place, here or here or here or here, or wherever. So we need to find out theta C1. So theta C1, you know how to find? Yes. Just divide this by this. Okay. So sine theta C1 by cos theta C1 is 10 theta C1. Okay, and divide the right hand side is minus 263 divided by minus 42.83. So this one minus 263.86 minus this one. So by finding this, we have got a positive value of theta 80.89, which is actually anti-clockwise if you take. So in this direction, you see 80, almost 80 degree angle. So this one will be here, MC1. Okay, this angle will be anti-clockwise direction angle, this is positive. So this is theta C1, okay, which is 80 degree. Okay, we have got to this 80. That's it, 80 point something, right? Something. So we have got the values of MC1, MC2, and their respective angles. Understood? So that completes your problem. One more thing, sorry. Uh, oh, yeah. Actually, I'm sorry. This is there's one thing. This is actually theta C1. Okay, that is actually for the reference. Sorry, for the resultant. I'm sorry. Here actually I have made a mistake. This part is the resultant. This is called the resultant. This is how we find the resultant. Okay, resultant. So this actually is a resultant balanced mass. Okay, I told you at the beginning that we have to take all the masses. This one, okay, the MC2, M2, M3 here, MC2 somewhere. We have to take their, we have to find their resultant. So their resultant is here at an angle of 80 degree point something. So if you place a counter mass to this at 180 degree away from them. So 80 degree is already is the angle, plus 180 degree in this direction is the counter mass. Actually, this is the location of MC1. Okay, this is actually the resultant of all the masses that we have transferred here. So that's why, sorry, that part is missed. This is just like the previous problem that we have solved. So before this actually in the class. So there we have added this angle to 180 degree angle to this one. This is not the same case with the previous one. Here you may ask, why didn't we add this minus 45 degree to this 360 degree? We have just subtracted it. Okay, actually that is like, you see here we have found this as what? In this case, with respect to reference plane, we have already found the angle. This is theta C2. So theta C2 is there. Okay, no need to place a counterweight here, because this is not the case here. Here we have actually transferred it here. That's why we have to find out the resultant. Here we are not finding any resultant. This mass is individually present. So we have not transferred any M1, M2, M3 with this one. Okay, so this is individually there. So we have found its angle. We have got a negative value, so that's why it is there, minus 45. So we have to find a positive angle, that is 360 minus this angle. That is separate thing. But here in this case, we have transferred all the masses, M1 here, okay, M2 here, M3 here, and MC2 also there. Then we have found their resultants, and the resultants makes an angle of 80 degree with horizontal. And you know, we have to place a equivalent opposite mass to the resultant. So this mass is placed at 180 degree. Opposite means 180 degree. So 180 degree plus the previous angle. That is what we have to do. Okay, this is what we have done already in our class. So that's why we have added 180 degree to this angle, not the previous case. In this case, in this particular case, this theta is actually theta C1. Okay, theta C1. So this is the angle. So finally, we have found value of MC1, MC2, theta C1, and theta C2. This completes your numerical. Okay. Next, we will discuss about balancing of reciprocating masses.